Progress.
All right. Uh, does anyone have any questions about the last homework? All right. If you go on Canvas, I uploaded a file. It's called calibration curve. Go ahead and download that. We are going to be running through how to analyze the data that's in there. And when you're done downloading the data, it should actually look like this. I'll show you what to do with it in a moment. But today, basically, I'm going to have you analyze the data, answer a bunch of questions that you can answer with that data, and then have you turn in something at the end of a class. And I'll end up putting that into the grade book. So with the data that we've got, it's for a calibration curve. A couple of the things we need to understand about the calibration curve and just a linear regression in general is it's valid over the range that you input. And this goes with any type of calibrate or any type of a regression model that you're using. If you calibrate, say, an electronic scale, and you look at it in terms of say 500 pounds, 1,000 pounds, 1,500 pounds, 2,000 pounds, and you get it perfectly calibrated in that range, that's the range that it's actually going to be good for. If you start trying to weigh things that are a lot lighter than 500 pounds or a lot heavier than 2,000 pounds, the scale might not work out that well, and you might get some odd issues coming up with it. The thing that ends up happening, uh, if we're talking about a calibration curve, I'm just going to pretend like a calibration curve is a linear for a moment. So let's say that's the curve that we're looking at. If you start measuring things that are out here or way out here, what ends up happening is you have essentially a 95% confidence interval that's going to look something like that. The area where or within the range has a really small confidence interval for it. Things well beyond that range end up having a much, much larger uh, confidence interval. Sometimes they can get to be so big that it's not even useful trying to measure anything out at that range. Uh, when it comes to some of the chemistry assumptions here, we assume that it's going to be linear between the ranges of when you look at the data, there isn't actually a data point for 0.00, but there's close to it, to about 2 ppb. And according to the quality control mangler at the company where I got this data from, the model should actually look like that. So instead of y equals mx plus b, we're going to be looking, or they assume that it's going to be y equals mx. 3, if you go, if you measure something and it comes out to be 2 ppb or larger, uh, you have to rerun that sample, but You also have to dilute it. And with these calibration curves, we're also trying to predict outcomes. So if we look at the data, what we've got is concentration. That's going to be a function according to this of some m value times the values that are in the TCMX column. This concentration is in parts per billion. Uh, the TCMX is actually area. So what we're trying to do is figure out what area times something can give us an idea about the concentration of whatever happens to be in that sample. That's where this predict the outcome comes in. We know the concentration and we see what the area is. Then we use the area to predict the concentrations. So when we have something that's called an unknown, or if we have a new data point, we can put in the area, and we can predict the concentration based on that. When we look at the data that we've got here, we can see that the area starts at about 5,000. And if it makes it a little bit easier for you to read, we can actually come up here, format the cells, and actually use a comma spacer. So you can see at the high end here, it's 1.75 million, and that correlates to a 10. Now, what we're going to do first, I'm only going to look at the values that go from 0.02 to 2.0. Just going to copy them and then paste them into Minitab. The last two data points here, going to copy and paste them elsewhere. So this is area that we're going to be looking at. And these are actual concentrations that we're going to be looking at when we try to make some predictions. So we've got our data. If you do a good job with these calibration curves, you get really good answers that you can use. And if we're talking about a business, you get the answers that you need, so you get a better reputation for being able to do a good job, that sort of thing. You also get a reputation for providing or not having to rerun samples over and over and over again. So the way that we're going to do this here is we're going to go to stat, regression, and then we're going to go to regression and then fit regression model. So once we've got to that point, our response here is going to be the concentration. Continuous predictor is going to be that TCMX column. And the model that we want to look at, because from chemistry theory, there is no constant. So we need to go to model and click off that include the constant term in the model. We can click on OK. And for right now, we're just going to go to graphs and do the 4-in-1, just like we did last time. Then you can go ahead and click on OK. And then the last bit here, I'm just going to go ahead and click on OK. And what we've got here is you can see in the coefficient table the approximate value that they've chosen for this. You can see the standard deviation for the model. You can also look at the R squared value in this case, 99.98. That means out of all the variability that's within the data, the model that we just created accounts for 99.98% of all of it. When we look down, we get the analysis or ANOVA table. This thing right here is trying to tell us that there seems to be a data point that might have a little bit high of a residual. So this is the difference between the predicted value and the actual value. When we look at the normal probability plot, does it look like all these blue dots fit along the red line completely? Not even close. When we look at the fitted values over here, does there seem to be, say, a pattern? Well, if you look, a lot of these are below the curve, and then we've got just one above the curve. So that's telling us that even though this model is 99.98% accurate, it might not be the best model we can deal with. Looking at the order down here, we get the same thing. Also looking at what is the range of values that we've got out here versus what we've got out here. Does this area here seem to be a little bit smaller in variability than the range of values we have out here? It does to me, which is telling me that a lot of the assumptions that we have about a linear regression just are not being taken into account with the model that we've got here. Sometimes that's important, sometimes not so much. Thing that we can do once we've got our model done, so we can go back to stat, we can go to regression, and we can come down to where it says predict. Because the whole point of a calibration curve here is literally to predict outcomes of unknown things. So we can go to predict, and it says enter individual values. I'm going to enter an entire column of values. I want to go back and use the model that we just made to predict the outcome of everything that we just looked at. So I'm going to look at options as well. Confidence level 95%, that's cool. Results, I want a prediction table. And I can click on OK. Storage, these are all things that are going to be populated down here in like column C6 through whatever. That looks good enough to me. Once I've done that, I'm going to go ahead and click on OK. And what we've got here, this PSE fits, we don't need to worry about that. But these are the predicted concentrations based on the model that we just made. These are those actual concentrations. So if you look here, the sample that we know was made to be a 2 ppb. We're predicting that it's going to be 1.9877. So is that good enough? Absolutely. When we look at the C-lim here, these are confidence limits, the lower level and the higher level. Does this confidence interval here contain the actual value that we're looking for. Yeah. Does this confidence interval contain the actual value that we're looking for? Yes, it does. Do these three actually do these 5 confidence intervals actually contain the values we're looking at here? No. So imagine that. Let's say you are trying to make sure that the scale at work is working properly. You put a 50-pound weight on it. You pull the 50 and you tell the scale this is a 50-pound weight. You then put the weight back, 50-pound weight back on there. And it tells you no. We believe that weight is actually 52 pounds, and the true weight of it is actually between 51.8 and 53.3. You just told it this is a 50-pound weight, and the scale can't tell you, or doesn't tell you that it's actually a 50-pound weight. It's overestimating it. Does that sound like a good model to you? Looking at the metrics, technically 99.98% accuracy, and it can't accurately predict what 5 of the 7 values that we just put in there. So what does that tell you? Maybe there's a little bit more to doing these than we thought. If we want to try to predict what's going to be happening with these 2 samples as well, can go back to start or stat, regression, regression, predict. This time we're going to look at the thing that I termed areas. We're going to go ahead and click on OK. And for the concentration that we know is actually 5 ppb, the predicted outcome is 4.48. The concentration that we predicted or we know is actually a 10 is predicted to be a 8.15. We look at the confidence intervals for both of these. Do they include 5 and 10? Absolutely not. So when it comes to a couple of the assumptions that we have here, what is all of this telling us? Well, one of the assumptions was the calibration curve is only valid in the range of data that we put into it. This is telling us that clearly data points that were outside of that calibration curve, it can't predict them well. But even data points that were used within the calibration curve, it can't predict them well. Looking at the data that we have, coming back to our graphs again, the way that this data is set up, or the way that this data is projected on here, looks to me, or is kind of a telltale sign that might be a quadratic or a cubic model that we need to use here. So what do we do with that? We can go back to stat. We can go to regression, regression, fit regression model. This time though, instead of telling the computer or telling the software everything, I'm going to let the software tell me what it thinks is going on. So I'm going to go back and I'm going to include the constant term in the model. I'm going to increase the terms in the model through 3rd order, because if there's a cubic function in there and it's statistically significant and it helps me do a really great job predicting the outcome, I'll use it. If it's not statistically significant, we can go back and remove it later. So terms through order, 3. I'm going to add all of those. Then I'm going to go back and click on OK. I'm going to leave everything else as it is. Go ahead and click on OK. And when we look at the data we've got over here, when we look at the R squared and R squared adjusted, we went from 99.98% accuracy to 99.99% accuracy. This is telling us that the linear term that we found is statistically significant, saying the quadratic term here at the 95% confidence level is not significant. I'll blow or open up this in Word so we can see it a little bit better, hopefully. So the 95% confidence level, is this statistically significant? No. At a 90%, is it? Yeah. So we might want to actually look at this. This is also telling us that this cubic term is not statistically significant. But these VIF values, in a good model, in general anyway, these values should be between 1 and 5, maybe 1 at 10 at the most. These look exceedingly huge compared to that. That's telling me that there's an issue with that sort of or with that VIF as well. This is basically measuring correlation between all of these different terms. So one way that we can work on that is to go back yet again and looking at the data again. Now it looks like there's a huge amount of variability on the left side, not much on the right. Do the data points here seem like they're a bit closer to the red line? Yeah. Are they perfect? No. So we can look at that again. Some of this stuff might not actually matter if what occurs. If the software is actually, or the model's actually good at predicting the outcome, do we really need to worry about anything much more than that? So again, go back to stat, regression, regression, predict. Let's see how good it is with our cubic model at predicting our outcome. Everything should be set as it was before, so I just need to click on OK. And I deleted everything that I'd done before. You don't need to. It's just this makes it a little bit easier for me to show you everything that we're looking at here. Looking at all these prediction intervals here, do pretty much all of these now contain the concentration that we're looking at? Yeah. The fits or the predicted outcomes, do they look a lot closer to the actual known concentrations that we had here? Absolutely. So in this case, we can actually say that using this cubic model is a lot better than using the linear model for predicting our outcomes. With this one, you put that 50-pound weight on the scale, it's going to tell you that comes out to be 50.5 pounds, and it's going to be somewhere between 49.1 and 51.8 pounds, which for what we're trying to do here is acceptable. Nothing's being overestimated, nothing's being underestimated. If we look at these last two data points, just to see what they do. So go back to predict. And then for here, go back to area again. I'm going to click on OK. And we look at what it's predicting for those two. We know that the concentration here is 5. This thing is predicting that it's going to be a 3.3. We know that this thing here is a 10. It's actually being predicted as negative 3.35. So something's definitely wrong with this. Are the true values within the confidence intervals? Yeah. But these confidence intervals here are way too large to be useful to us at all, which is telling us that this cubic model that we've got here is actually a much better model than we had before. But when we start getting values that are outside of it, uh, it might start to fool us or trick us into thinking that it's a value within the range here when it's really not. So that's telling us we need to go back and redo all of this yet again. So again, I'm just going to delete what I've got on there. So now go back to stat, regression, regression, fit regression model. For the model, I've just double clicked on the cubic term. So now we're just going to look at a quadratic model. Let's see how this changes things up. Everything else is going to be essentially the same. So I'm going to come up here and click on OK. So we eliminated that cubic term. The R squared adjusted value is 99.99. So the same accuracy we had before. The VIF for our model is a lot lower than it was before. It's a lot larger than ideal. And we notice that the p-value that we have here is still above 0.05. But again, what we're trying to do here is we're trying to predict an outcome. And when you have a large VIF like this, that means that these coefficients here are actually larger than they should be. And they're 14.6 times larger than they should be. The larger the standard error, or the larger the perceived standard error, the harder it is to actually determine if something is statistically significant or not. So let's go back one more time. Go to stat, regression, regression, and predict. Let's see what happens with this particular model. So with this new model, again, I'm going to try to predict the outcome for everything that we've already looked at. Going to go ahead and click on OK. Looking at these fits, these are, again, the predicted outcomes for everything we've got over here. Are they fairly close? Yeah. Are the true values for every single one of these concentrations within the confidence interval that we have here? Yeah. So this is already looking like it's just as good of a model as the last one. Let's see what it does with these new things out here. So regression, regression, predict. Then for this last one, Going to look at the area one more time. Going to click on OK. The predicted outcome for the standard that was at a 5.0 is 4.73. And it's actually predicting that the concentration is a little bit lower than it really is. It's predicting that the concentration of the other standard, which we know is a 10, is 9.1. But 10 is within the confidence interval. So that's kind of telling us that yet again, the model that we have here is a lot better than the first model we had. It's a lot better than the cubic model that we had. But is it working well enough? At least in the range of data, it is. When we try to extend it a little bit, maybe not so much. But the idea here is we're trying to figure out what model should we be using with the data that we have here. So the couple more things that we can do with this is because we were looking at this table of coefficients, the VIF here is fairly high. We can go back. We can run yet another model. This time we need to look at coding. And I'm just going to do something simple and say subtract the mean. And then I'm going to click on OK. Now that we've got all of that, I'm going to go back and click on OK one more time. I know this is all boring, but this is literally how you do this sort of stuff the right way. Go back, you're constantly testing over and over and over again. By subtracting the mean, the VIF is now 3.47 instead of 14. So this is more in line with what we would expect from a reasonable regression model. The R squared adjusted value is 99.99, so it's still really high accuracy. The blue dots that we have are very close or a lot closer to the red line that we have here, meaning that it's more than likely normally distributed, which means it's a lot better of a model than we had before. Still going to be an issue out here with the variance, because the variance out here looks very different from the variance out here. But what is the important thing for all of this? How well does it predict? So one more time, we go back to regression, predict. We want to look at all the data again. Click on OK. And essentially, the values that we have here and the values that we have out here are pretty much the same as we had before. So this new model is just as good at predicting outcomes as the old model. It does a really good job trying to predict the actual concentrations of everything as well. And with a model like this, again, we're going to check these last two data points, see if there's anything that changed with that. I don't think there will be, but you never know. And since it is literally that easy to do it, why not do it? So again, the fits are about the same as we had before. It's still a little bit low, predicting the 5.0 ppb standard, but it actually hits the 10 ppb standard. So when we look at essentially everything that we've got here, we now have to go back and try and figure out a couple things. What is the model that we should actually be using here? What does the best job for us? Or what is the uh, best thing that we can actually do? So again, looking at, come on, looking at some of the assumptions, according to theory, our calibration curve is only valid within the range of the inputs that we have. If we force it to be this linear regression model, we find that it actually can't predict a bunch of the standards that we put in there accurately. So maybe we need to question whether or not we should be using a linear model like this. There's an assumption that if you have those standards that were at 5 and 10, if you use the model, it's not going to predict them well, which means you need to rerun them and dilute them to try to get the concentration in those vials into something that's within the uh, predict or the range of the values. And then we're also trying to predict the outcome. And with that model, like I said, we've already found it doesn't do a good job. So should we be using this model? And literally, if you look in a like a chemistry or an engineering textbook on this thing, or on these types of calibration curves, this is what they're going to tell you to use. Is it correct? Yes or no? We've already seen that it doesn't do a good job, so should we be using it? Right. So what's the model that we should be using with this type of data? Well, we saw that the quadratic model actually worked out fairly well. Even though when we look at the results, and we can look at it with where we subtracted the mean or not, one of these terms, so that quadratic term on there, looks like it might not be statistically significant at the 95% confidence interval. But how many samples do I have there? I've got 7 data points. Uh, like I was saying in previous classes, if you've got small sample sizes, should you be sticking to 95% confidence interval at all times? No. Smaller sample sizes, go with, say, 90% confidence interval. 20, 30, 40 samples per group, 150 to 100 samples overall, go with the 95. Start getting into thousands, if not hundreds of thousands, go with the 99. If we use that idea, should we actually keep this quadratic term in there? Yeah. When we look at this, what is the outcome, or what is the model that we should be using? So I'm just going to go with the original data. Oops. Sorry, that's going to go with this data. So basically, what's going on here is the model that we have, and the model that if we want to do a good job, if we want to save ourselves some time, we want to save ourselves some money, we want to get accurate results, it's going to come out to be y equals negative 0.00, so 0068, plus, you can see right here, 1, 2, 3, 4, 5 zeros. So 0.1235 times 5, and then times area, or you can call that x, whatever you want to call it, plus, and then what did we do with this coefficient here? Can you even see what that coefficient is? Out to 6 decimal places, it's 0. So unfortunately with this, and if this happens to be on an exam and I'm asking you what is the model we should be using here, your answer would be 0.003456 x squared, or in this case, we could call it area squared, depending on what we want to go with. So what is the model we should be using? Whatever that is. Once you've got that model, you can then go in, start looking at unknown samples, start plugging in some of the values, and start seeing some of the weird things that actually go on. Next week, we're going to take this type of idea, bump it up a notch or two, and then we'll see what's actually going on with that. And don't close Minitab just yet. But there is another couple quick things I want to talk about with these types of regression models. But what we were just doing, looking at everything, is we're doing our hypothesis tests. From a statistics point of view, the model that we looked at originally is something like this. We're looking at our original hypothesis, beta 0 equals beta 1 equals beta 2 equals beta 3 equals 0. Our alternative hypothesis is that something does not equal 0. When I put the beta n down here, that n just stands for a number, because next week on Thursday, we're going to have another data set where you're going to have 20 or 30 different variables to look at, and trying to write them all out is going to be a pain in the butt. From what we just looked at, from what we've discovered, is that our final assumption is going to be essentially beta 0 equals 0. Where does that come from? Well, looking at the data, what's the p-value for the constant here? And that's well above 0.1 or 0.05 or whatever value you want to use. So we can say that the constant here is not statistically significant. With these other two, we're going to say that they are. So beta 1, we're going to say does not equal 0. Beta 2 does not equal 0. And beta 3 does equal 0. So that eliminates what we've got there. And we should also eliminate what we have out here. A lot of times, though, if you're with some of these statistical models, you're going to leave the or beta 0 in there anyways, even if it's not statistically significant like what we were doing. Technically, it shouldn't make any difference, but there are times when you can, if you go back and do basically what we've been doing, run all the models with the cubic term, then run all the models with the cubic term with out the constant, run all the cubic models with the constant, but make that a change of subtracting the mean, and then run all the models without that. Eventually, you're going to come up with a model that works a little bit better than what we've got. Does anyone else want to spend the next 2.5 hours going through all of that? Didn't think so. So, but this just gives you an idea of what it's like to be an actual statistician, an actual data analyst. You look at everything, you go through, you evaluate this, you look at the assumptions. Sometimes, even if an assumption is violated, you can still say, well, it's a good model because it does the job we need it to. So, which is what we're doing here. Does that make doing this work a lot more confusing? Absolutely. How do you get over it? Uh, well, when you look at your paycheck, you go, oh, okay, I'm fine with that. I can get over it easily. Um, so we just with this one data set, and if you look at the time, it's already been 45 minutes and we've done what? We looked at one simple data set and we didn't even get it completely analyzed completely properly. So imagine what it's going to be like if you try doing this with the data set like I had to deal with looking at 120,000 different vehicles trying to or figure out what are the quote unquote drivers of poor performance and warranty repairs, and then having to go through, use multiple modeling methods and multiple uh, and use each of those modeling methods multiple times in order to come up with a subset of variables that may or may not have a significant impact on predicting whether or not a vehicle comes in for warranty repair, so that the company I was working for can then turn that into a computer program, which can turn that into a green light, yellow light, red light system for, do we let this vehicle off the plant grounds? Yes or no? Yeah. So big time stakes like that can get into a lot more complicated things than we're doing here. Uh, but with what we've got here, we've figured out what our model's going to be, and now we can go back, we can start predicting things. One of the things that happened as well, uh, essentially using the same instrument where all of this data came off of. And when I ran the calibration data like we've got here, I actually knew about this issue. So I did everything to make the running of these samples, tried to make sure that they were uh, with the least amount of bias, using all the ideas and assumptions we had with our regression models, which are what? One of them is everything has to be, or samples have to be independent of each other. We've talked about if I ask all of you to, like, say, stand up and tell everyone in the class, how do you feel about something? You're all going to have an opinion because you need to. Is that truly the opinion that you have? Maybe, maybe not. Why would you change it? Peer pressure. I don't want to have an argument with that person about how they feel about this particular thing. So I'm just going to say, whatever. Agree with them, make it easy. That way I don't have to talk with them. Another way that we can have an issue with this, and this is something that actually does come up in production plants and happens all over the place in all sorts of different businesses. One of the issues I had was when I'm looking at the data, and we already kind of looked at the quality control data on one of the earlier homeworks. when I plot some of the data that we'd use for quality control. Go up like that till it's about ready to go beyond the control level. Shut the instrument down, start over again. Starts out low, goes back up high. Shut it down, start it over again, goes down low, comes back up high. Well, what was happening with uh, in this particular case, and this is actually similar to a problem that will be on exam number 2. What you could do is each one of these is considered a run. And this one is in the first run position. This one's in the second run position. This one's in the third, fourth, and so on. And what we ended up with was the response is equal to about 70% plus, I'm going to say 4% times the run position. So if run position is number 1, the response ends up being 74% of what it should actually be. If we have something, so this is at run position equal to 1. If we have something at, say, run position 20, 20 times 4%, so that's 80%. 80% plus 70%. The response that we would get from this particular instrument would be 150% of what it should be. So again, this is like, imagine you've got this 50-pound weight, or let's say a 10-pound weight, you put it on the scale. The first time you put it on the scale in the morning, it comes out as 7.4 pounds, not 10. 20 times later, you put that 10-pound weight on the scale and it says, no, it's 15 pounds. So 150% of what it should be. Does anyone see an issue with this? What do you think? If you're working in a company and you are measuring things by weight or by volume or something like that, and the devices you're using are telling you, oh, it's the same amount every time, but the first time you do it, your 10-pound sack of potatoes is actually 7.4 pounds. The 20th time you do it, your 10-pound sack of potatoes is 15 pounds. Anyone see an issue with that? If you're the consumer and you're getting the 15-pound sack of potatoes for the price of a 10-pound, awesome. You're the person getting 7.4 pounds of potatoes when you're paying for 10, that's fraud. So one of the things that you can do with the data like this is you can actually use this type of information to go back and correct things. So in this particular case, we were working with highly toxic chemicals. On anyone here into real estate at all? Or looking to get into real estate? Okay. So if you are going to be, say, buying a building, or if you're going to be an entrepreneur and start your own company, start your own business, one of the things that you can do, you don't necessarily have to do it, but for personal protection, it is a good idea. Is get the property that you're going to be developing tested for a bunch of different nasty chemicals. If it's found that the concentration of these pollutants on the property is above a certain level, then it's on the current property owner or former property owners to actually remediate all of that. If you decide not to do that testing before you purchase the property and someone comes in, purchase the property after you and finds that there's elevated concentrations of stuff, even if it wasn't your stuff, you're the last, or you are the last owner, you are the one responsible for it, you are the one that is going to get sued, and you are the one that is going to lose and have to spend potentially millions of dollars cleaning up a mess that wasn't yours. But you saved 5 grand at the beginning, so it's all worth it, right? So imagine if uh, we've got two different samples, and let's say these samples just happen to come out, and we know that they're the same concentration because the company we're dealing with decided to test our analytical capabilities. But when we analyzed them, this sample right here, what is reported is 80 units. And because of this, we know that that's going to be 74% of whatever's actually in there. With this last one, let's say it's reported as 110 units, but we know that that's going to be at 150% of what it really is. How do we go back and correct these? So these are what is reported. What is the actual number of units of contaminants in both of these, number one? And two, let's say if you have 100 units plus, it's toxic and someone's going to have to clean it up. If it's below 100 units, let's say between 80 units and say 99 units, you tell whoever it is, you give whoever it is a warning. You tell them, hey, it's close, but according to what we've got, uh, you might want to look into this a little bit further. And if it's a 0 to 79 units, it's technically below the toxic level, so it's fine. Is the land contaminated? Yes. But is it contaminated enough that you, as whoever's going to develop the property, needs to spend money to remediate it? No. Is anyone fine under knowing that say your backyard is contaminated, but it's not contaminated enough to be harmful, so don't have to worry about it? Does that sound reasonable to anyone? Well, it is actually how these things work out. So if we're looking at these types of things, and all we look at is what is reported initially, what do you tell the person from this first run? So I will say A and B. Just based on the values that came up on the screen without doing any of this investigative stuff that I did, uh, the instrument says there's 80 units of a material in there. Is it toxic? Do we give them a warning or do we tell them, oh, it's completely fine. Go about your day, you're good. We give them a warning, right? The people down here in part B, 110 units, that's in the toxic area. So we tell them, hey, you need to spend millions of dollars remediating the ground that you're building on. Well, if we go back and make corrections based on what we have here, what are the actual concentrations here going to be? formula that we can use here is the reported concentration is going to be equal to whatever percent we were dealing with times the actual concentration. So we want the actual concentration. We have the reported values. We have the percentages. So what do we do here? Just divide both sides by the percentage here, right? So with both of these, what we end up doing is you take the reported value. So in this case, it's going to be 80 units. And divide that by the percentage. We have to put this in as a decimal. So 80 units divided by 0.74. Here, 110 units divided by 1.5 because it's 150%. What values do we get from that? So as soon as the calculator starts up, come on, there we go. Good calculator. So 80 divided by 0.74. The actual concentration here is going to be estimated as 108.1. Up here, 110 divided by 1.5. So 73.3 units. So what do we notice here? If we didn't do these, if we didn't calibrate or know about these issues here, what are we telling the person A? It's a little bit elevated, but you should be fine. You might want to watch out for it in the later. What is it really? It's toxic, right? So we tell the person that's got toxic levels, it's okay. We tell the person who has levels that are in the fine area, hey, you need to spend millions of dollars. If you're that real estate developer, if you're that entrepreneur that just bought that property and you spent, say, $250,000 remediating the soil and you didn't have to, how do you feel? Seriously, probably want to sue somebody, right? If you're the person that bought this property up here and you're told, well, it's a little bit elevated, but it's not at the toxic level yet, so you should be fine for now. But it is actually toxic. Again, what do you want to do to that the company that did this testing for you? Probably sue them, right? And with the company that did or did these types of testing, uh, if there is a lawsuit, what do they have to do? They have to go into court, and everything that they did and everything that they did wrong eventually becomes public documentation. So imagine if you're the company that does this testing and you screwed up not once but twice in the same day, and you get sued twice in the same day. Do you think your company is going to stick around for very long? Yeah. So if you're the business owner, what do you want? You want to make sure that you've got a really good calibration curve going so you can accurately predict all these things. What's another thing you want to do? You want to have a really good quality control manager who's looking at these things and going back. And even if they know that these things are happening with your the instrumentation, being able to go back and recalculate everything to give the best possible answer. Kind of important to know that, right? And where did all of this come from? One stupid data set with seven different uh, calibration curve values. And the company that I worked for, that where all this data actually comes from, are they still in business? Did they basically get sued out of existence? Uh-huh. Was I there when that happened? No. But based on what you all know about me, what do you think I said when I heard that they were sued out of business? I laughed, right? So again, uh, everything we did with the calibration curve, was that boring? Yes, yes, it was. But is it worth it? If you get it right, you can avoid all these things in the future. You get it wrong, you do the, well, I expect it to be this, and literally what happens with a lot of this stuff when you're doing the calibration curve, you are telling the data what it's going to tell you. We're looking at it and we're asking the data to tell us what it wants to say. A little bit different approach. So, with that said, uh, hopefully everyone kept their uh, Minitab open. So this is going to be the part where you actually turn something in today. So go to regression, regression, predict. And this time, instead of entering a column of values, enter individual values. Uh, check out 80,000 and 800,000 and let's say 8 million. And what I want from you is basically going to be a table. So we've got an area of 80,000, 800,000, and 8 million. What is the p-fits? So this is predicted concentration, and CLIM and CLIM 1. So this is the uh, lower confidence level and upper confidence level. So once you've got those three values in here, you got everything set up, go ahead and click on OK, and everything will be spit out for you. All right. Hmm? So basically, I want 9 values. All right.